everyone, my name is Adam Thomasson and I'm a postgraduate researcher at the University of Manchester in the UK. Today I'd like to talk to you about domain walls in the two-Higgs-doublet model, which are a type of topological defect that may have formed at the electroweak phase transition in the early universe. And the work I'm going to present was performed in collaboration with my PhD supervisor Professor Richard Batty and Dr. Stephen Cotterill of the University of Manchester. Before I begin, I'd just like to thank the organisers from Early Universe from Home for giving me the opportunity to present my work here. So, domain walls are a type of topological defect of the vacuum manifold that can form in the early universe if a discrete symmetry is spontaneously broken during a phase transition. Now, I can demonstrate this idea with a simple scalar field with the potential of the form shown here, where as the universe cools, that scalar field will randomly populate two degenerate vacuum expectation values in causally disconnected regions. Now, as the universe expands and those causally disconnected regions come into contact, continuity of the field requires that there's an interpolating sheet-like structure between regions of opposing vacuum, and this is what we call a domain wall. Now, if stable domain wall networks were to form, they would rapidly come to dominate the energy density of the universe, which is in conflict with cosmological observations, and this is known as the domain wall problem. So therefore, any phenomenologically viable network must eventually decay. But this decay would create a transient out of equilibrium environment which would have potential observable consequences. Now, domain walls are commonly studied in toy models with a single scalar field which respects the discrete symmetry of the vacuum. And that single scalar field would interpolate between the two degenerate vacuum expectation values. But more realistic models, such as beyond the standard model theories, are multi-field theories, and that means that you can have additional degrees of freedom which can be active inside the defect but still respect vacuum constraints. So this could lead to the possibility of local symmetry breaking or confined currents to the defect, and the 2HDM is a concrete example of this richer vacuum structure. Now, the two-Higgs-doublet model is one of the simplest extensions to the standard model of particle physics, which introduces a second complex doublet to the scalar sector, which predicts the emergence of 5 physical scalar particles as opposed to the single scalar particle of the standard model, which is the Higgs boson. It retains the standard model gauge structure and the fermion content, but this simple extension to the standard model changes the possible structures of the vacuum manifold quite drastically. Now, the general model has a very diverse vacuum structure with a rather complicated potential, which I'm not going to show here. But you can restrict the parameters of the potential such that it satisfies different so-called accidental symmetries. And if the model realizes one of those accidental symmetries, the topology of the vacuum determines which defect type might form if such a symmetry were spontaneously broken during a phase transition. Now, commonly studied example symmetries are a Z2 symmetry with a discrete vacuum structure, which leads to domain walls forming, a U1 symmetry, which leads to strings and vortices, or an SO3 symmetry, which can lead to monopoles. Now, stable examples of each defect have been classified and shown to exist in the literature. But here I focus on the Z2 symmetric case, which admits domain walls. My colleague Dr. Cotterill is going to be presenting a talk focused on vortices and monopoles within the model. Now, imposing a Z2 symmetry is actually phenomenologically preferred because it can eliminate tree-level flavor-changing neutral current particle interactions, which are rather heavily observationally constrained. Now, before talking through the domain wall solutions of the model, I should first talk about the scalar field structure. So, as I said earlier, the 2HDM has 2 complex doublets, phi1 and phi2, which means that there'll be 8 degrees of freedom in total in the fields. Now, a useful representation of the fields, which we use in this work, is to decompose them into so-called vacuum manifold parameters, F1, F+, F2, and Xi, acted on by a general electroweak rotation, where sigma naught is just the identity, VSM is the standard model vacuum expectation value, which is a fixed number, and U is an element of U1 cross SU2. Now, there are many different representations you can use for this electroweak rotation, but we use one that's useful here for domain wall solutions with fields gamma 1, eta 1, 2, and 3, which again leaves us with 8 degrees of freedom of the fields in total. But we actually find that domain wall solutions in the 2HDM actually only require 6 scalar fields to describe them fully. As if you solve the Euler-Lagrange equations with the condition that the domain wall solutions have a finite energy in the vacuum, then you find that eta2 and eta3, those electroweak group parameters, can be described fully by the 6 remaining scalar fields, f1, f plus, f2 xi, gamma 1 and eta 1, which means that you only need 6 scalar fields to fully describe any general domain wall solution of the model. And I'll actually show in the slides to come that the individual domain wall solutions actually have an even further simplified structure, but we'll get to that. So, because all measurements of the Higgs boson, which was first observed in 2012 at the LHC, show it to agree with the standard model prediction, the 2-HDM needs to preserve this. And so we do this by identifying one of the CP-even scalars, little h, in our analysis, with the standard model Higgs boson. And when you do this, it means that the only 3 parameters of the theory are the masses of the heavy scalar particles, h, a, and h plus minus, and the ratio of the vacuum expectation values of the 2 complex doublets, resulting in only 4 total variable parameters of the model on which the domain wall solution are going to present the bend. And one final thing before I demonstrate the domain wall solutions is to understand that there are actually 2 distinct classes. So firstly, we have a minimum energy domain wall solution, which means that all fields have Neumann boundary conditions associated with them, which means that they're the lowest energy state, which satisfies the equations of motion. They're dynamically stable, and the fields interpolate between the degenerate vacua, minimizing the gradient and potential energies. These are inherently the domain wall configurations towards which the defects will dynamically relax to in the early universe. And you can see a demonstration of the form of the boundary conditions you impose on the solutions here. And then we also have another commonly studied type of solution called electroweak rotated domain walls. So these are when there's a fixed relative electroweak rotation between the 2 different vacua, which are higher in energy and are generally excited states of the minimum energy solutions. But they're physically relevant because during a cosmological phase transition, different regions will populate the vacua completely randomly. And so you'll have 2 opposing regions which are related by an electroweak rotation. It takes the form of the boundary condition shown here, where in the electroweak group parameters there is, for example, a fixed rotation between them. So these types of solutions would be a sort of transient state, which form during a phase transition, but they will then relax towards the minimum energy solution. So it's important to understand both types. So we've actually found that the minimum energy domain wall solutions can be described by 3 distinct subclasses, which are determined by the scalar mass hierarchy and tan beta, the doublet vacuum expectation value ratio. And these are so-called standard, superconducting, and CP-violating, which are all described by simplified field configurations. So the key scale to bear in mind is which of the scalar masses, mh plus minus or ma, is the minimum. And once that's been evaluated, one finds an instability threshold above which the domain wall solution of minimum energy is simply this standard solution, described only by f1 and f2, with the other degrees of freedom being energetically driven to 0. Now this threshold here simply brings in the other scalar masses of the CP-even particles, mh and m little h, with this f1 to the minus 2 at 0 needing to be evaluated numerically or semi-analytically in certain regimes. And it simply describes the value of f1 at the center of the domain wall, which, based on effective mass arguments, basically determines if any other additional degrees of freedom will be active within the defect. And that itself depends on the vacuum expectation value ratio. So below this threshold, if the charged scalar particle mh plus minus has the lowest mass, then we find that a charged condensate is energetically favourable within the defect core, with an interpolating profile in gamma 1, which comes about due to that further lowering the energy density of the solution, with the other parameters xi and eta1 again being energetically driven to zero in this case. In the opposing regime, where the CP odd scalar is of the lower mass, then we find that the defect has a locally CP-violating form, with the CP mixing angle xi interpolating between the two distinct vacua and changing value throughout the defect. And in the case that the two masses are equal, we actually find that these two distinct types of solutions, superconducting and CP-violating, exist simultaneously. So we can better demonstrate the local symmetry breaking effects of these solutions by considering the bilinear scalar field formalism, R mu, which describes fully the potential of the model and is, in terms of the fields we've already considered, takes this form here. Now, we see clearly that the Z2 symmetry breaks in R1 in these domain wall solutions, but some other interesting symmetry relations are if R mu is zero, that corresponds to the electromagnetic symmetry being unbroken. Now, in the superconducting regime of our solutions, we see clearly that R mu develops a non-zero component at the center of the defect, which means that at the center of these solutions, the photon actually acquires a mass, which has many interesting phenomenological consequences. And in the case of the CP symmetry, which is described by R2 being equal to zero, we find that clearly within the CP violating regime of our solutions, that R2 develops a non-zero profile locally inside the defect. So, as I mentioned earlier, there's actually another class of domain wall solution relevant to a phase transition in the 2-HDM, which are the relatively electroweak rotated vacuum solutions, which can be described by the following boundary condition, quite simply, with the fields at negative infinity being in the negative vacuum and at positive infinity being in the positive vacuum, but with an explicit electroweak rotation applied between them, with the electroweak rotation taking the form as I showed earlier. So the effect of this can be best demonstrated by noting that all of these solutions here have the same scalar particle masses and tan beta ratio, so the same parameter set. We see that the minimum energy solution in this case is described by the standard solution with only F1 and F2. However, if we act upon that with a explicit gamma 1 rotation, we see that R mu becomes non-zero in the defect, with the electromagnetic symmetry being locally broken. And again, if we rotate the vacuum with only eta 1 here, we find that an explicit CP violating core solution exists. So these electroweak rotated solutions do simply correspond to excitations of the relevant minimum energy solution. So up until now I've been classifying static field configurations, but importantly the question is, do they actually occur dynamically? And the answer is yes. So here I'm showing snapshots of simulations of a phase transition in the 2-HDM, and we see that in each of the respective solution regimes, where the standard solution, superconducting or CP violating is the minimum energy, that the minimum energy solution indeed dominates the dynamics. For example, in the superconducting solution regime, we see R mu locally non-zero upon the walls, and in the CP violating solution regime, we do indeed see R2 being locally non-zero on the domain walls. We also note that the electroweak rotated excitations are present, for example in the standard case where neither symmetry locally breaks in the minimum energy solution. We see a mild breaking of the electromagnetic and CP symmetry. In addition, in the superconducting regime, we see an even milder CP symmetry breaking, and in the CP violating regime, again, we see a mild electromagnetic symmetry breaking. And this shows that the dynamically present domain wall structures can be perfectly captured by the classification of solutions which I've been presenting. So, having established that these distinct domain wall structures do form dynamically during phase transition simulations of the 2-HDM, the natural next question is what consequences might they have? And on the particle physics side of things, local symmetry breaking could lead to a variety of interesting interactions. For example, states of bound gauge bosons in the superconducting regime, which could lead to interesting decay channels, or asymmetric particle scattering, such as top quarks scattering into bottom quarks in the CP-violating regime, which has been explored by a group at DAISY in a related scenario. Now, the particle interactions with these domain wall solutions is currently an ongoing area of research for myself, and I hope to be able to provide insights into that in the future. Another active area of research of mine involves the possible cosmological observables of these domain walls, especially with the detection of a stochastic gravitational wave background by the Pulsar Timing Array Consortium in recent years, for which domain walls provide some convincing fits to the data. Now, some recent work that has appeared on the archive has suggested that current carrying domain walls may exhibit distinct gravitational wave spectral features, such as additional peaks in the spectra, and the different scalar particle masses of the theory may also leave imprints on the characteristic frequency scales of gravitational wave spectra. So this provides a potential avenue for constraining the 2-HDM mass hierarchies and the viability of the model through observations of a stochastic gravitational wave background, for example. So I'd like to briefly finish off by talking about some further extensions of domain walls within the 2-HDM. So we can in fact use these superconducting solutions that we found to construct two-dimensional analogues of cosmic vortons, which are closed loops of current carrying string, known as kinky vortons. So we do this by adding a current, shown here, to the superconducting ansatz of the domain walls and wrapping that into a closed loop with a winding N in the charged condensate, as you can see here. Now, this current acts as a stabilizing force against the wall tension and stabilizes the loop against collapsing. Now, we find these objects to be stable, oscillating with a natural frequency about a given radius with a conserved winding number N and charge Q. And this demonstrates the viability of vorton-like objects in a minimal extension of the standard model. Our future work by myself and my colleagues is going to involve the construction of vortons in the U1 symmetric version of the theory, and we hope to be able to show that these kinky vortons provide a way to consistently explore the parameter space of the model in a more computationally tractable setting in 2 dimensions. A further novel domain wall configuration that we find in the 2-HDM is that of a maximally CP-violating wall, where we find in the CP-violating regime that where the Z2 symmetry is restored on the wall in R1, it can actually break again in R2, with the CP symmetry being maximally violated along the center of the wall. And we further find that these local walls can support themselves a charged condensate. And if these local walls were to form closed loops upon sheet walls in 3 dimensions, then you can imagine 2-dimensional objects such as kinky vortons actually living upon 3-dimensional domain wall networks. And this would lead to both electromagnetic and CP symmetry breaking effects as the domain wall network evolves. The 2-HDM doesn't just exhibit domain walls, but a complete hierarchy of structure defects, currents, localized CP violation, all emerging from a simple extension to the standard model. So to conclude, I hope I've been able to demonstrate to you all that the 2-HDM admits a remarkably rich spectrum of domain wall solutions that can be rigorously classified by the relationships between the scalar particle masses of the theory, these walls supporting local electromagnetic and CP symmetry breaking effects with a wide variety of phenomenological consequences and possible ways to constrain the 2-HDM through cosmological observations. I'd like to thank you very much for listening, and I very much look forward to the live discussion session later in the week.